Now, let us go on and talk about a case where we are going to talk, we do have a periodic perturbation, but we are going to treat that not using perturbation theory, but exactly. And we will see that that case validates the approximations that we are, or the perturbation theoretic approximation results that we have found so far. Now this is a case where you are going to discuss a sinusoidal perturbation again, but in a two-level system. So we have a two-level system where the energies of the two levels is separated by E0. So by choosing the zero of energy appropriately, the H0, which is the Hamiltonian for the unperturbed system, essentially has two diagonal elements. Half E0, that's the upper state which we denote by plus, the ket plus has energy half E0, and the lower state, the ket minus, has energy minus half E0. So that's simply shifting the energy so zero, so that the average of the two energies is what we call what we define to be the zero. So that's my initial Hamiltonian. This obviously has two eigenkets, plus and minus, namely 1 0 and 0 1 as column vectors, with energy eigenvalues half E0 and minus half E0 respectively. On top of this, we have applied a perturbation V of t. Ignore the double equals, this of course should have been a single equal, which is purely off diagonal. Basically our F operator that we talked about is the operator 0 F 0 0. F dagger of course is 0 0 F star 0. So this is what my V of t is. It's a Hermitian operator made out of F and F star, where F and F star are constants. So what is my H? H is simply the sum of these two, and we change our notation a bit. Instead of E0 we write H cross omega 0. E0, remember, is the energy gap between the two states, and that we write as in terms of the frequency omega 0, and F we write as half H cross omega 1. To do that, you can take an H cross by 2 factor out, and this is what your matrix looks like. Omega 0 minus omega 0 comes from here and here, and omega 1 into the minus I omega t is simply F into the minus I omega t, except for the half H cross which I have taken outside. Now, if you look at this matrix properly, this matrix after all is a Hermitian 2 by 2 matrix, traceless Hermitian 2 by 2 matrix, and all traceless Hermitian 2 by 2 matrices can be written down in terms of the sigma matrices, sigma 1, sigma 2 and sigma 3. And in this case it's very easy to figure out what the expansion is. The omega 0 times sigma z, that's where the 1 0 0 minus 1 is coming in. Omega 1 has a cos omega t here and a cos omega t here, so omega 1 cos omega t is multiplied by 0 1 1 0, which is of course sigma x, and omega 1 sin omega t has a minus I factor here plus I factor here, so that's multiplied by the matrix 0 minus I 0, that's your sigma y. So this is what the Hamiltonian is. So it's basically H cross by 2 sigma vector, which is of course matrix valued vector with components sigma x, sigma y, sigma z, dotted with another vector with coefficients omega 1 cos omega t, omega 1 sin omega t and omega 0. So this is essentially the problem of a spin half particle in a rotating magnetic field. The spin half particle is assumed to have a magnetic moment of minus g mu, and if you put it in a rotating magnetic field which is given by a fixed component in the z direction and a rotating component in the xy direction. So it's a vector which is going round and round the z axis, with b perpendicular given by this b1 cos omega t and b1 sin omega t factor, where h cos omega 0, this coefficient, and h cos omega 1 simply can be related to the b0 and b1. So this is straightforward. If you put a electron or any other spin half particle with a charge, of course, with a magnetic moment in a uniformly rotating magnetic field, you are going to end up with this Hamiltonian. While this Hamiltonian describes sinusoidal perturbation applied to any two-level system, we have a direct physical example of that, which is simply a spin-half particle in a rotating magnetic field. And that example, of course, is very, very important technologically. Things like NMR, nuclear magnetic resonance, ESR, electron spin resonance, all of these basically start with considerations of this, a magnetic moment in a rotating magnetic field. Now this is a problem which I claim is exactly solvable. So how do you exactly solve it? Well, let's set up some background first. This is something we had described earlier in a different context, but let's talk about this again. Remember, what we want to do is solve the time dependent Schrodinger equation. IH cross del psi del t is ht psi t. So we want to find out psi of t. But what we do is, we try to simplify the problem by finding out psi r t. This is really a change of picture, like when you change from Schrodinger to Heisenberg or Schrodinger to interaction picture. Just to remind you, changing over from Schrodinger to Heisenberg picture essentially makes the time evolution problem trivial as far as kets are concerned, because then the kets no longer time evolve. Well, we are not going to do something as drastic as that, but we are going to change to another ket psi r t by putting in a time dependent operator r of t acting on psi t, and try to see what kind of Schrodinger equation psi r t obeys. And that's pretty easy to figure out. I just try to calculate IH cross del t of psi r t. This of course is going to be IH cross times RT times derivative of this plus dr dt times this. Simple standard rule that is applied for products all over in calculus. And now you realize that IH cross del psi del t, this thing here, is nothing but H acting on psi. So if you put that in, this first term becomes RT HT psi t. The second term of course is IH cross dr dt psi t. Now since I want an equation in terms of psi r, a Schrodinger equation so to speak for psi r, the fact that there is a psi t on the right hand side is a problem. I want to replace this with psi r t, and so all we do is write psi t as r inverse psi r t. I perhaps forgot to mention that before, but we are assuming r of t to be invertible. Actually we are assuming it to be unitary, so invertibility comes with that anyway. So once you throw that in, you get this whole thing in the bracket in front of psi r t. So it's IH cross del t of psi r t is some operator acting on psi r t, and that operator is of course what you call the effective Hamiltonian for this particular picture. So the HR, the R picture Hamiltonian, is given by RT HT R inverse t plus IH cross dr dt R inverse t. So if we often can cleverly figure out R of t so that HR becomes either small or simple, then my life becomes easier as far as solving the Schrodinger equation is concerned.
So now that we have this general setup ready, how do we use this for the specific Hamiltonian at hand? Well, just to remind you, this is the Hamiltonian for which we want to find the time evolution. And as we talked about a while ago, the physical picture here is that of a spin-half particle with a magnetic moment in a rotating magnetic field. So it seems natural to think that if we were to rotate the coordinate system at the same rate as a magnetic field is rotating, then in the new coordinate system the magnetic field will look like a fixed vector. And the problem of a spin-half particle in a fixed magnetic field is one which we know how to solve exactly. So given this background, it's natural to choose for R of t an operator which will cause rotations about the z-axis at a rate omega, namely this particular R of t. Now let us see whether actually choosing this R of t helps? Well, we need to calculate HR, the R picture Hamiltonian for this particular R of t, and for this we need this quantity IH cross dr dt R inverse. It's very easy to see that if you were to differentiate dr dt, you will get I omega by 2 sigma z down. R inverse of course will cancel whatever exponential is left, and in addition to that you have an IH cross in the front that will give you the minus half H cross omega sigma z. So that was straightforward. What about RH R inverse? To figure that out, it's better if we look at R sigma I R inverse for I equals 1 to 3 separately first. Well, RT sigma z R inverse t is obviously sigma z, because RT, this particular R of t, commutes with sigma z. So it's going to move right across sigma z and cancel the R inverse t here. That was easy. What about sigma x? Well, to calculate RT sigma x R inverse t, we need to use the Becker-Hausdorff lemma that we had discussed before, and if we use it, it's pretty straightforward to do the calculation. We will end up with sigma x cos omega t minus sigma y sin omega t. Given the fact that R of t produces rotations about the z-axis, this result should be pretty obvious, at least easy to understand. And what about sigma y? Well, RT sigma y R inverse t is going to be the same rotation acting on sigma y, so sigma x sin omega t plus sigma y cos omega t. There's a typo here, this should be sigma y. Okay, now if we take all this and plug it back, first of all let's calculate RT H R inverse t. That means in this H, of course you're going to put RT on the left, R inverse t on the right, and because these H cos omega 0 are just numbers, RT R inverse are going to act essentially on sigma z, sigma x, sigma y separately, and once we put all of that in and use the magic of trigonometry, that is cos square theta plus sin square theta equals 1 and stuff like that, this whole thing will simplify very much. I urge that you take pen and paper and work this out, and you will end up with RT HT R inverse t is simply H cross by 2 omega 0 sigma z. This term of course doesn't change under R inverse, but this term simplifies a lot and becomes just omega 1 sigma x. So something which is a constant, the time dependence has been cancelled as expected. Of course this is not the full Hamiltonian HR. For the full Hamiltonian you need an additional IH cross dr dt R inverse term, which is plus minus half H cross omega sigma z. So you end up with H cross by 2 omega 0 minus omega sigma z plus omega 1 sigma x. So as promised, once we have applied this R of t, we have gone into a new picture, and in this picture the Hamiltonian HR of t, the effective Hamiltonian in this picture, describes the interaction of a spin half particle with a constant magnetic field. So since this Hamiltonian is a constant, the time evolution problem for this psi rt is equal to urt0 psi 0, that is finding out the urt0, the operator which is going to carry out the time evolution, is trivial. urt0 is going to be simply the exponential of minus I by h cross the operator hrt. So it's the operator hr which is being exponentiated here, of course, but the important thing is hr is time independent, so the simple formula works. So by substituting HR, this is what we have to exponentiate. Now the properties of the sigma matrices that we have studied earlier tells us how to do this very easily. In particular, it told us that if I had this thing, if we exponentiated minus I theta by 2, where theta is any real number, into sigma dot n hat, where n hat is a unit vector. Of course, sigma vector here is just a vector whose components are sigma x, sigma y, sigma z. Then the result is simply cosine theta by 2 I2 minus I sin theta by 2 sigma dot n hat. If you have forgotten how this result is derived, let me just remind you of one thing. You can easily show that sigma dot n hat whole square is the identity. That means, of course, any even power of sigma dot n hat is the identity, and any odd power is simply sigma dot n hat itself. You just use this result,
and use the definition of the exponential operator in the form of an infinite series, and you can immediately read off this final result. Now in this expression, of course, we do have sigma vector dot n hat. Well, you have sigma vector dot a vector, that is sigma x, sigma y, sigma z is being dotted with omega 1, 0, because there is no sigma y, and omega 0 minus omega. So these are the three components, omega 1, 0, omega 0 minus omega, of the vector which is being dotted with sigma. Of course, that is not a unit vector, but that's easily remedied. You find out its norm, divide by that, and then you're done. So the norm of the vector is simple. It's just you just take this vector and find its norm. You can immediately write down the result, where this capital omega is nothing but the norm of the vector omega 0 minus omega comma 0 comma omega 1 by 2, and this capital omega is the driving thing in this oscillation. As you can see, you have cosine capital omega t, sine capital omega t all over the place. So capital omega, which is half of square root of omega 0 minus omega whole square plus omega 1 square, is what normalizes this whole vector. And now once we have this, ur t0 is known, but we want to get back to psi of t. Psi of t, of course, is r inverse t psi r t. So that's r inverse t ur t0. So this combination r inverse t ur t0 is the actual Schrodinger picture time evolution operator, us t0 psi 0. We already have an expression for ur t0 in terms of the sigma matrices. We already defined r in terms of the sigma matrices, sigma z in particular. So the multiplication of r inverse with ur is not that complicated a thing. It's slightly messy. If you carry it out in full, you will get us t0. However, all that we really want to figure out here is what is the probability that a system which was in the ground state or the lower energy state, the state minus to begin with, evolves into the state plus. And for that, thankfully, we don't even have to do this multiplication. Notice the transition probability that we want is simply this. The state minus, the lower state, is what you start from. You apply us t0 on that, which is the time evolution operator, which takes you from time 0 to time t, and that this us t0 minus gives you the state at time t. And if you want to find out the probability amplitude, that there is a plus state in the result, that the system has been excited to the upper state, you take the bra plus and hit us t0 minus with that. That gives you the probability amplitude. You take the modular square of that, you end up with our probability. So this is what we need to calculate. Now, as I said, us can be found out by applying r inverse first, and or rather r inverse second, because the one on the left actually gets applied later. But you need us t0, you need this form. Us t0 is r inverse ur t0. However, r inverse sitting here would have acted upon the plus eigenket, which is an eigenket of sigma z, hence an eigenket of r inverse as well. Remember, r inverse is made only out of sigma z, and it's easy to see that all that this will give you is a phase factor. So if you take the mod square, that phase factor will simply give you 1. So you can simply forget about the distinction between us and ur for this purpose. So you can directly work with ur t0, find the plus minus matrix element of that, take the mod square of that. Now what is the plus minus matrix element of ur? For that, let us go back to the expression for ur that we had here. Notice that this term is diagonal. Of course, it's just the identity. Sigma z is also diagonal. So both of these two terms are free of a plus minus matrix element. The plus minus matrix element actually only comes from this. Omega 1 by 2 divided by omega times minus I sine capital omega t. So that is the thing whose mod square will give you P fi, the transition probability. So that's it. The transition probability from the initial state I to the final state F is given by omega 1 square by 4 capital omega square sine square omega t. So as I said, this capital omega is what is driving the oscillation. The frequency of the oscillation is given by capital omega and it's called the Rabbi frequency, this capital omega. Now as you can see, what this is telling me is that periodically the probability of occupancy of the higher level is going to go up and down. It's never going to reach 1 as long as omega 0 and omega are different, because as long as omega 0 and omega are different, capital omega is more than omega 1 by 2. So this is going to go from 0, the system entirely in the ground state, to a superposition state where there is a high probability of finding a particle in the excited state, the system in the excited state, and then it's going to come down again, and all this is going to happen periodically. These are what are called Rabbi oscillations. Of course, you can rewrite the omega 1 in terms of the original matrix element capital F, and now this form also tells you one thing. For small times, omega t can be, sine of omega t can be replaced by omega t, and then this simply gives you the result that we had before. Although this result PFIT is an exact result, for small times it gives you PFIT is approximately f mod square by h cross square t square, which of course is a quadratic growth of the probability that we talked about earlier. Also notice that at large times the further terms in this expansion would actually cut in, and hence this probability is not going to increase without bound. Of course it can't, being a probability, but the exact formula does show you that for small times you do get the result which we obtained by first order perturbation theory, and for long times is going to take over from this t square growth, is going to end up being an oscillatory thing. And a special interest is the case when you have resonance, that is when omega 0 equals omega, that is the rate at which the system is rotating, the magnetic field is rotating, exactly matches the energy gap between the two levels. Then what happens is capital omega is exactly equal to omega 1 by 2, and now this is what you are going to get. PFIT is sine square, there is a typo here again, sorry, this is going to be sine square omega 1 by 2 into t. But capital omega, again, that's the Rabbi frequency in this case, is now just omega 1 by 2, and you are going to get nice oscillations, and these oscillations are going to carry you all the way up to the excited state. So here what we see is periodically you will find a time at which the system is entirely in the excited state. Then it will come down again to a superposition, and then finally to the ground state, back again a superposition and the excited state, and so on. So these are the kind of oscillations which are very, very important technologically. They are especially important in the context of nuclear magnetic resonance and or electron spin resonance, where this theory plays an very important special role. Now, so far we have been talking about transitions to discrete levels. This last example was a very special case where you have just had two discrete levels, a system with only two levels. A slightly more complicated situation arises when the level that the system transits to is part of a continuum of levels. This continuum of levels requires slightly different ways of thinking about normalization of the states and so on. This is a very important special case, and we will devote the next lecture to that. Bye for now.